Okay, and I'm now recording. So, can we start? Or should we wait a little bit again, more? I think, yeah, Matteo, you were...
We can start. I don't know. It's it seems for me there are like yeah, Moit, yeah, Daniel. Yeah, let's. I mean, yeah, let's start and then like let's see.
Okay, the dream team is here, so it's okay.
Yes, exactly.
So, so today it's not about what Timeflux is and what it can do, but more about how to do things. I think we already covered the features of Timeflux in a previous presentation, but of course, if you feel you are missing something, please let me know. And I know you all come from different backgrounds, so I will try to find some balance and get the basics covered. Maybe some of you will get bored and will find, other will find things too technical, but don't worry too much about this. There are different ways of approaching and using Timeflux. Maybe you are a neuroscientist or a researcher. You can do DSP, or you are a developer, backend developer, or front-end developer, UX designer, whatever. There are room for everyone here. And also, when we do workshop with Rafael, mostly we do this offline, so with the people in the same room, and we can, go behind the back and check the screen, etc. So it's a little bit different today. We can't really do this, and because also we are missing this maybe interaction, it's a little bit difficult also to have hands-on exercises. So today we will present a goal-oriented workshop. So we will go through basic theory, the bare minimum you need to know, and we'll check and show you some code, how to write a basic neurofeedback application, and then we will give you homework. So if you are interested in continuing to work with Timeflux, and we will give you hints on how to improve the application and how to get to have some hands-on on basic digital signal processing with an exercise that was done by Rafael a few months ago. And of course, today is mostly about this basic neurofeedback application, so we go into details into it. But if we need more details, or if you have specific needs, we will have time to discuss this into more details. So I will assume that you already have Timeflux installed and you already played at least just a little bit with it, but if not, it's not a problem. And so yeah, before we start, I'd like to ask you a few questions. I don't know why I can't see you guys, but it seems that if I'm sharing my screen, I can't see you. Hi, Sachin.
Hi.
And I see Bar is connected too, and Anza. So yeah, cool.
Hi, Pierre.
Hi, Bar. Okay, so I can't see you, but I can hear you at least. So feel free to answer my question. So have you installed Timeflux?
Yes. Matteo, yes.
Yeah. Or you can use the chat. I think I can have access to the chat. Okay. So it's okay. And Bar, yes, we are recording. Okay, so Hamza, yeah. I saw you posted a message on the Slack. I don't know if you got the answer. Okay, so it's not a big deal today, and we will go into. You don't strictly need to have it installed today, and also I know it can be a little bit complicated if you're not used to Python, etc., and you're not a developer. But we recently worked on a proof of concept of binary. So there is now currently it's only working on macOS, but soon you will be able to just have one binary on your computer. You click on it, and everything is self-contained, and you can launch an application easily. So, but if you need, we won't spend too much time getting it installed today. We can devote some time to answer question at the end, but by experience, I know it can be tiresome to get it installed during a workshop, because some people have everything already on the computer, and some other it's exotic configurations. Sometimes it's more complicated. So don't worry if it's not installed. We can see that later. So for those of you who installed Timeflux, have you followed the tutorial on the documentation website?
Some of it. I had some trouble with getting a local host to work still.
Okay. Interesting. So you were able to install Timeflux UI,
Yeah.
but you couldn't have access to the interface from your browser.
Yeah, it says you can't connect.
Okay.
But
maybe do you have a local firewall or something?
not that I know of. I just did a clean install.
Okay. Okay, we cannot trouble us on this.
But,
maybe the port is already in use or something. Did you have an error message in the console?
Right now I'm getting it started, so I wanted you to keep talking, and then
okay. Cool.
But before lunch there was no error. There was no error message in the console. It just said couldn't connect.
Okay, and you just in case you know that we'll see how we can do this later, but you can change also the port and the interface. So maybe you have also several interface. I don't know if you're okay, and you are on Windows, Linux.
Ubuntu, yeah, Linux, Ubuntu 20.
Okay, so yeah, localhost is.
Okay, but we can come back to it.
Cool. So okay. So I'd like to also to know if anyone is not familiar with the YAML syntax.
So I'm not a particular programmer, but I think I'll be happy to pick up on it. I've used Python, just very, very, very basic aspects of Python. So as long as I can run it on Python and understand it. So I don't think you have to put too much effort, and I can try to maybe learn it up myself eventually.
Okay. Yeah, it's YAML is really not that complicated. And if you go on the tutorial page on the documentation, on the Timeflux documentation page, there is a link to a video, short introduction to YAML. It's not complicated.
Okay, super. Thank you.
Okay, and also, who has some experience with Python? Okay. Okay. Okay, perfect. And okay, and if you don't, it's not an issue. So it's again, there is a lot of way of approaching Timeflux. Python is mostly useful if you want to develop your own plugin. And Raphael, I know you have experience with Python. And Raphael is the one who developed most of the DSP nodes in Timeflux. And speaking about DSP, digital signal processing, who has at least maybe not experience in developing tools, but experience in using DSP techniques or know some basic theory about digital signal processing? Okay. Okay. And again, depending on how you want to approach things, it's not something that is absolutely required. I'm just trying to see what is your background so I can orient the discussion more easily. And last but not least, who has experience with web development, that is HTML, JavaScript, CSS, that kind of things, or PHP for Matteo, and maybe Perl also. Okay. Okay, so great. So let's continue. And first, a few things. Maybe you can print. Of course, everything is recorded, but if you want to refer to this later, maybe you can take a screenshot of this slide. This is what you will need. So of course, there is the Timeflux website, the documentation website. We have a tutorial here. We try to cover the basics and to have the basic theory behind the Timeflux here. We are on the Slack. We have a Slack channel. So if I'm not here, maybe sometimes Raphael is here or Sylvain, and we can answer your question if you have any question. And for today, we will work on a basic neurofeedback application, and you can download it at this address if you want to follow along. And if you don't, it's okay, because I will share my screen and you will be able to see the code yourself. But if you want to download this, you can use the last address, and I'm giving you like 30 seconds to download this. And Matteo, no, it's not required today that we join the Slack channel, but maybe I will give you homework. Yeah. Okay. And during the time we'll see when we do the next workshop, but during that time you will be welcome to ask any question you have on the Slack channel. Okay. So before we continue, I'd like to give you some just a little bit of theory. I guess most of you are familiar with the time series, but just so we are all on the same page, this is the textbook definition of a time series. That is a series of data points indexed in time orders. So there are different ways of displaying, of having a representation of time series. So here it's EEG with 4 channels. On the left, it's represented in a tabular way, and on the right, it's plotted. So we can see the 4 channels, and on the left, we have the index, the time index. In Timeflux, we use pandas for 2D time series, and we use X-array for multidimensional time series. And sorry, just one thing, Raphael, feel free to unmute yourself at any time, and if you want to say something.
Yep, I'm not muted.
Okay. Okay, so this is time series, and in Timeflux, so Timeflux is a framework which allows you to build applications. So what is a Timeflux application? A Timeflux application contains several components, and the first one is the pipelines. So the pipelines, it's graphs. We will see later what is a graph, and it's the basic computing unit in an application. It's the minimum that you need in an application. So what it's used for, it's used to acquire some data from a device, to process the data in some way, and to output the data. So output can mean many things. You can send it to a WebSocket and display it in a browser. You can record it on your computer, or you can send it through the network to another application. Another component of an application is a configuration file. And usually you can configure your pipelines using environment variables, either directly in your console or in a file. And sometimes you want to have a very specific node, a very specific piece of code that will do signal processing. So we already have many DSP nodes, but sometimes you have one specific need and you want to write it. And you're not expected, you can of course publish something on the pip repository or something, but you can just have also one Python class and put it in your package. So it's really easy to do. And we'll see later how we can write custom node. And you can also define a user interface. And the user interface, usually we use JavaScript, HTML, and CSS. But it's not absolutely required, because in the pipelines you can use another network protocol, and you can send the data to another program. Maybe you can use 0MQ or LSL to send the data to Unity, or you can use OSC to send the data to Pure Data, which is a program to play sound. So another thing you need to know is that each pipeline is running in parallel. So when we have multiple pipelines in an application, each pipeline runs at its in its own thread, in its own process rather, and each pipeline runs at a specified rate. That is, maybe if you have a device, maybe you will run it at 10 Hertz. 10 Hertz means you run the whole acquisition pipeline 10 times per second. And so if your device is outputting data at 100 Hertz and your pipeline is running at 10 Hertz, that means that each time the pipeline is running, you will get 10 samples, okay? And to ease your development, there is a few things you need. So we have set of helpers, functions, and debugging tools to facilitate development. We have plugins. So plugins are just Python packages that expose additional nodes, custom nodes. And we have branches. Branches are pipelines that runs into one single node. It's very useful when you don't want when you want to reuse different nodes from different plugins, etc., and put it neatly into one node so it's easier to use. And also it has a big advantage because you can use your pipelines as branches offline. That means that when you work on a new DSP pipeline or a machine learning pipeline, or you want to test everything offline in a Jupyter notebook, for instance, it's easier to use a branch because then you don't have to rewrite everything to do it real time. You just reuse your branch and you use it online. It's no change. You don't have to rewrite everything. Okay, so remember we talked about pipelines. We talked about configuration. We talked about custom nodes and the user interface. So we go into details on each of these components. So pipelines. Pipelines are basically graphs. Graphs, we describe the pipelines, the graph in using a YAML syntax. We'll see in a few moments how we can do this. And the graph is composed of nodes. Nodes are the computing unit in a graph. And for instance, there will be a node to connect to a device and get data from a device. Another node to window the data, that is cut the data in small chunk, overlapping chunk. Maybe you will have a node to do machine learning, a node to send data through a socket, etc. Everything is a node, basically. Edges connect nodes together, and ports are the connection point between nodes and edges. And ports contains inputs, they provide inputs and send outputs. And the data that transits through ports is twofold. So first we have tabular data, 2D or n-dimensional data, and we have metadata that describe the data, basically. And so we support two kinds of inputs and outputs. We support data frames from pandas and Xarray. So in a more graphical form, this is a graph. So I think most of you already saw this in the previous presentation, but just as a reminder, this is a graph, a directed acyclic graph. If you have done some basic computer science, you see that this kind of graph is everywhere. And so a directed acyclic graph is a set of nodes connected by edges where information flows in a given direction without any loops. So if we flatten this graph, we have what we see on the screen. And this is the topological order of the graph. That means the first graph to be executed will be on the left, then the second one, etc. And all the arrows are edges that connects port together. We can see that we can send an output to another port forward in the graph. Some nodes have several inputs, others have several outputs, etc. So, you know, when we talk about neurofeedback, there is the notion of feedback. that is notion of loop. And we just said that a directed acyclic graph doesn't allow loops. So how can we do to create artificial loops in this kind of graphs? We can do this by using an asynchronous way of communication. And so we use a protocol, a messaging system, messaging protocol that is called publish subscribe. It's not something we invented. You can find this on the internet. Publish subscribe means that some nodes will publish data to a broker, and some other nodes will subscribe to the data. And that means that when you see, for instance, on the second graph in the yellow box on the bottom left, the second node of this graph is publishing data. So one of it's a publishing node, basically, and it will send data to another graph, which contains only one node, broker. And this broker is responsible to manage subscription from other nodes and to keep the data while it's available, etc. And on the first graph, the first yellow box, you can see that there is one node which subscribe to a topic. Okay, so subscriber express interest into a topic, and publisher publish information data to this topic. This is very interesting because that means also that there can be multiple publishers writing to the same stream, and of course multiple subscribers listening to the same stream. Okay, so just one last bit of theory. It's about ports. We have different kind of ports in Timeflux. The basic Timeflux port is the default port. Each node has one implicit input and one implicit output. And there will always be one input and one output. Even if you don't use it, there will be the default ones. You have also named ports. If one node is expecting more than one input, you need a way to identify the ports you're interested in. So you can give it an identity, a name. Some ports are dynamic. That means that they will destroy themselves after each update. One prime example of this is the epoching node. So an epoch, when we do an epoch, we capture chunks of data, and sometimes because the graph run at a given rate. So if the rate of the pipeline is low, we will accumulate several epochs in one run. And so we need to have multiple ports so we can dispatch each epoch on different ports. So we can do this in a dynamic way. And the last thing, yeah, okay, so it's the number of ports is just a variant of dynamic ports, but I don't want you to worry too much about this right now, and it will make more sense as you progress, and when you encounter specific needs, you will understand why it's important. Okay, so let's get started with a quick example. So if you follow the tutorial, you have already seen this. I will just give you a general overview of this. And we will just do the first part of this tutorial. This is the helloworld.yaml file, the basic, the most simple scenario, the most basic pipeline you can do with Timeflux. And everything is detailed on the tutorial webpage on the documentation site. So feel free to go there and follow along if you want, and you take the time you need to explore this. But this is an opportunity for me to show you how the syntax we use to describe graphs. So as you can see on the right, we have one graph, one pipeline with 3 nodes, and each node is connected by one edge. Okay, so on the left, the first thing we notice is the graph list. And I'm not sure if you can see my, my mouse here, if I move it. Okay, cool. So we have the graph list, and basically in YAML, you organize your syntax by indenting. So you see that everything here is one tabulation. So everything is a list under the graph. Okay, and so in this graph, the graph has 4 properties. The first one is the ID. We give a name to a pipeline. It's not mandatory, but it's very useful when you want to debug and you have more complex applications. Because when you output something in the console and there is an error or something, you can the name of the pipeline will be displayed, so you will see where the problem comes from. Another component of the graph, another property, is the nodes. Here, the nodes is also a list. We also have edges, and we have a rate. Okay, so the nodes are the individual computing units in our pipeline. Each node also have multiple properties. So they have an ID, a module, a class, and some parameters. Here, in this case, nodes have an ID, and the ID is mandatory in nodes. Why? Because later we need the ID to connect the nodes together. Then we have a module. The module is, as you can expect, is the name of a Python module. So you can use any module installed in your system. And the class of your module. The class has parameters, and these parameters are passed to the constructor. So here you just have a random node that will generate some random data, and we say, okay, give me 5 columns, that is 5 channels, and each time you generate some data, there will be between 1 and 10 lines, and each value will be between 0 and 5. And here we give it a seed to initiate the random generator. It's not mandatory, but if you do science, you know that reproducibility is very important and that you want to have the same results every time. Okay, and then we have another node. Here, this is the add node, and what it does, basically, it gets the value from the matrix generated in the random node and add 1 of each of the value. Then we have a display node. It's just a debugging node. that will display the data on the console. Okay, so this is our node property. Then we have the edges property. And in the edges properties, we have a list of 2 elements. And this is how we connect the nodes together. So we connect the random node, the add node, and the add node to the display node. The last component we have is the rate. And the rate is here, it simply means that we will run the graph at once per second. So I think there is some background noise, so I muted everyone, but if you need to say something, feel free to unmute yourself. Okay, maybe we can try it and see how it works. So here is my console. Oh, okay, I'm not sure where I put this graph actually. Okay, so it's not exactly the same, but it's really kind of, yeah, it's the IDs are not the same, but it's basically the same nodes. And so what happens when I run this nodes, this pipeline? So the D parameter is for debugging. So that means that I will, it will show, it will print more things on the screen. So, okay, what happens here? So of course you can see anything. I will interrupt with Control C. So each time the graph is updated, so once per second, it generates random data and it displays it on the screen. Okay, Raphael, so see you later.
Yep, see you. Bye.
Bye. And yes, Matteo, there is a list of all the available modules, and they are on the documentation website. Look into the API section and the plugin sections. Okay. I think we basically covered the essential things about a graph, about a pipeline. There is much more that you can do with pipelines. There is a tutorial again. You can follow. There is something that is very useful when you have complex application. You can have imports, and that allows you to cut your application in several parts, and you import and reuse parts of applications. And we have templates. We use Jinja for those of you that are familiar with Python. Jinja is a templating engine, and it allows you to add logic and add configuration directly into your YAML file. So you can add conditions and you can replace values by environment variables, etc. And of course, there are many nodes and plugins, and you can find the list on on the documentation website in the API section and the plugin section. Okay, so before we go to the next topic, does anyone have a question about the syntax, the YAML syntax? And don't forget that you are muted, so if you have something to say, unmute yourself first. So should I assume that everything is clear then? Okay. Thanks, Hamza, for the support. Okay. So next topic, if you want to write custom nodes, custom DSP node, and this allows you to see how you can write your own logic, your own processing nodes. So this is one example node, and this is the node we used in the example just before. And here we will take an input and we will add a value to each cell in the matrix, and we will send the result to an output port. Okay, so as you can see, this is just a basic standard Python class, and the Python class extends the node class, which is defined in Timeflux. Again, if you're not familiar with Python, don't worry too much about this. You will need this only if you want to develop your custom nodes. And so the init method is the constructor. So this is where you pass the parameters. So remember here we have a param subject with the value key, and we pass the value 1. So that means that in the constructor here we will have, in value we will have 1. Okay, so what we do, because we are in object oriented programming, we store the value we received in the constructor. We saved it in the class instance, and each time the pipeline is updated, this function, this method is executed. And this is when you define a new node. This is the only method you need to implement. It's the update method. And yeah, there are a couple of other methods you can use, mostly to do cleaning. There is a terminate method, this kind of thing, if you want to do cleanups a bit before the pipeline exits. But basically, the most important thing is the update method. And so what we do here, we have always, remember, a default input and a default output. Input, the name of the default input is I. The name of the default output is O. And because these values are stored in the class instance, we refer to them with the keywords here before. And ready here is just a syntactic sugar to make sure we have something in our input. And if we have something, first we copy the output to the input, and we add our value to each of our output. And when we just need to set our output like this, and everything else is taken care of. So yeah, and of course so we use here the default input and output. But if you wanted to give to write to another output, for instance, you can call it whatever you want, and it will be created dynamically as long as it starts with I or O underscore something. Okay, and again, the last thing is that ports contain a data object. So in this case, it's a data frame, and we use this convention of describing the name of the input and what it expects and what it provides. And this is also important because in the next future, we will use this docstring to automatically generate tools to graphically build interfaces, so we can know exactly what kind of input and output is expected and provided in a node. Okay, and so this is just one node, but if you want to have multiple nodes, or if you think that your node is covering some important stuff and you want to publish it on the web, etc., what I recommend is to publish it into a standard Python package, and we provide a template that you can reuse to publish, and it contains everything, including the CI/CD pipelines, etc. So testing and validation, etc. And it's a template you can use, and you're good to go. You just have to overwrite the default example, and you're good to go and publish it. Okay, and the next topic is about the JavaScript and HTML application framework. But before we go there, does anyone ask question about custom nodes?
I had one question for custom nodes. How, if I want to, like we were talking the other day about the ML, custom ML node. So how would you go about integrating an external library into this?
So what about the machine learning node?
Like suppose you wanted to include another library like PyTorch or TensorFlow, how would you go about including it into this?
Okay, so you need to take several things into account. If you want to have a machine learning node, you need first you need to train data, and you need training data, and then you need data you will work on. So either you can use one stream for training data, one stream for testing data, and maybe you can have only one for both, and then you would have another stream that will contain events, another input that will contain events, and you will react to what you receive to in this event data stream. And for instance, you could receive an event saying, okay, training is starting, training is stopping, and now I want to another event when you are ready to to test data, etc. And also you will have parameters to tell you, to say if you are doing some regression, if you're doing some classification, if you are working with 2D data, n-dimensional data, it depends, etc. But so machine learning is not the simplest topic you've chosen, but we do have a machine learning node, and everything is based on scikit-learn, so it's completely compatible with scikit-learn. And from my experience, as we already discussed this, but deep learning on EEG data is
may not be the best option.
Yeah, today it's we have very good results with Riemannian geometry, for instance, and we can do everything in it's very quick to use and not much computing, etc. But if you wanted to do machine learning, deep learning, maybe we will need a lot of data from different people at different times, because the thing is with EEG data, you can't really train a model for one people and expect it to work for another subject. And even more, you can't expect to have a model trained for yourself today and expect it to work with you tomorrow. And there is a lot of variation between individuals and between moments. And so that doesn't mean it can be done, because it has been done, but we don't have the computing power required for obtaining the same results as a very simple algorithm is several order of magnitudes. And so maybe, actually, it's one of my dreams to have something like an ImageNet, but for EEG data. And I think what we will need is to have many data sets with different EEG systems, different users, different electrodes, and different conditions, and train a super network on this. And then we could just have a minimal training and do transfer learning on the last layer or something. I think that would be one way of approaching deep learning in Timeflux, at least with EEG data. For other purposes, maybe ECG data, which are much more predictable, I think we can train a generic model, probably.
The main question is that, like, can I find any kind of code where you've actually used something like scikit-learn? Like, I want to know at the very least how to include any external library, like that includes scikit-learn. So as a code example.
Yeah. So there is, give me 1 second. The thing is, I have rewritten the machine learning node not that far ago, and it's not very well documented. But I think there are, oops, what did I do?
I understand exactly what you're saying about EEG, but so yeah, I think it's best to use that algorithm. I just wanted to know, in case we, if we plan to use this for anything else also, it'd be nice to include an external library of it, whether it's any algorithmic.
Sorry, I haven't heard your last 1 and 2 sentences.
It would, I mean, having an external library integration would be good for any application.
Yeah. Yeah, I agree. And honestly, this is something we need to do for deep learning, This is something I have on my to-do list, but we really need to think what we want to achieve with this. And yes, Matteo, we can do a machine learning workshop later. And I'd like to do something maybe with a real BCI like a P300 speller or something like this. Or maybe SSVP, I don't know, but yeah. The idea, basically what you need to retain right now is that if you are able to have a model, a Acyclic model that works offline, it will work online with Timeflux, no problem.
Okay.
And we, as I need to provide a few examples because I don't have a lot.
Okay.
But you can see you can check also the unit test to see how it works. Okay, and this is the code of the machine learning node. So it can work with multiple dimensional data. It can do prediction. It can do classification. It can do regression. It can work on continuous data. It can work on epoch data, etc.
Great, got it. Thank you.
And it can resample if you transform the data rather than public. So you can basically do everything you can do offline with scikit-learn, you can do it online.
Okay.
And I will just give you also. So sorry for everyone who is not familiar with machine learning, but it's interesting to, maybe it's an advanced topic for now. But Vijay, if you want to look at it, here are the unit tests for the machine learning node. So there are quite a few tests, but it should see how it works with multiple data, two-dimensional data, basic transformer, regressor, and classifier, etc.
Got it. Thank you.
Okay. So let's go back to something maybe a little bit easier for everyone. It's how we can have JavaScript application. So how we can receive data and send data and do web applications. So again, web apps are one way of building application with Timeflux. You can use any of the available network protocol, and of course we can use Barsage. I haven't forgot, and we will implement MQTT in the future. And for now we don't have MQTT, but we have 0MQ, we have OSC, we have LSL, and we have also basic TCP nodes, and so you can do a lot of things. And for the 0MQ, we support many way of representing the data. So we use we can use JSON or whatever is easier for your application. But here we will focus on applications that run into a web browser. So we have a JavaScript API. And with this, we can build applications and user interfaces. And this JavaScript API allows you to receive and send data and events, and allows you to deliver precisely timed stimuli. It's not an easy task to do in a web browser. And you know that if you want to do EEG research, ERP research, or SSVEP, you need to know exactly when the stimulus was displayed on the screen. So one way of doing this is to have a screen that refresh as fast as possible, and so you have some kind of tolerance. But what we do is the inverse approach. So we can use any kind of screen, even a low frequency screen, and a standard screen has a 60 Hertz refresh rate. That means it's refresh 60 times per second. And that means that 1000 divided by 60 is about 16 or 17 milliseconds, 16 or 17. That means we should have a precision of 16 or 17 milliseconds. That is totally unacceptable when you want to do ERP research. And this is why what we do is we schedule events to be refreshed, to be displayed on the screen. And when the screen refresh, we send the event. So we know exactly when the screen has refreshed, and so we can align the time with the refresh rate. So you can do ERP research, you can do SSVEP in a web browser. And you know, even in a traditional screen, SSVEP is not an easy task. Most people prefer to use LEDs and that kind of things. But we had a demonstration, and maybe for a next workshop we will show you how to have a MP3 player, for instance, that you can control in your mind, with your mind. And yeah, so the JavaScript API is available from the Timeflux_UI plugin. And if you go to the Git repository, there is an example directory, and you can find many pipelines to show how it works. I think most of you have already seen that, but I can just give you a quick overview, maybe for you, Daniel. So for those of you that worry about the console interface, the terminal things, all these lines, etc., I'm not familiar with this, don't worry too much about this. This is the way I like to do it, but as I said earlier, there is a graphical user interface with everything but the in it, and it's a work in progress, but we already have a prototype. So I'm just running the demo, and I have a web browser somewhere. Yep. Okay, so several things. So sorry if I'm repeating myself, but I think everyone has not seen this. It's just will illustrate what you can do in a few examples. So the first thing we have is, and this one is embedded directly with the Timeflux UI plugin, is a monitoring system. So here I have random data, and I can just display the data. I can also send events from here. So right now it's a CPU based, but I'm working on a new version with will use of the GPU, and which will be more modular, so we can also see the spectrum, etc. So it's a work in progress, but this is working already pretty well. Another example is the control center, and this is totally configurable when you run experiments. You want may sometimes record things. Okay, here is the full name, but maybe in an experiment it will be a random ID and an email. You can have here just nothing, but just an example. And all these fields are configurable. And oops, I hope you can hear me. It seems my connection is not that good.
Yes, we had a moment of interruption, and yeah, we couldn't hear 10 seconds of what you said, but I think we are there now.
Okay, cool. So what I was saying that this is just an example of a control center, and everything you see on the screen is fully configurable in the YAML file. And so here we can also send events. So for example, if you are running an experiment and there is a load now in the room, you want to record it, and then it will be recorded along the data. So later when you analyze the data, it will be easier to see why the data is weird or something. Another thing is just a basic EEG signal quality index. So here again, it's random data, but just an example to show you how we can receive data and we can display it. And this is really an example, a simple example, because the code for this is really there's not that much code. And okay, so this is the HTML, and this is the JavaScript code basically. And I receive data and I display it, and it's just an SVG file. And I will show you exactly how we can use this code later. But again, this example was, I think I've done this in like 20 minutes or something, and most of the time was to find an image SVG on the web. So, and the text isn't clear. I don't know. Maybe my connection is not that good, and Vij, and the streaming is not good. I don't know. Is it just Vij, or can you see my screen correctly, everyone? Okay.
It's a bit blurry.
Okay, maybe my connection is not very good. I can try to.
Yeah, it seems very. I can't read anything.
Okay, sorry. So I think my connection is not very good then. Okay. Anyway, I'm nearly finished with this, and for this for the next one, you won't need to see text. And the next one is how to have a repeating stimulus, which can be used for SSVEP research, for instance. And so, okay, it's just a way of displaying a stimulus at a very, very precise rate. Another example, which is a full-blown example, maybe we will have a workshop on this later. Okay, wait, sorry. And so this is a P300 speller, and this is how we can spell something with our mind. So first there is some little bit of calibration, then we train the machine learning model. And so I was asked to focus on the letter T. And then I'm asked to focus on the letter R here, etc., etc. And each time the letter I'm focusing on is is displayed is in blue. Then there is something, a spike we can see on the brainwave about 300 milliseconds later. That's why we call this the P300 speller. And we can classify this with a machine learning model. Okay, I won't go to the end, and of course I don't have any EEG set on me, so it's just random data, but just to show you basically how it works. And the next thing we use, and I often use, is another example is the oddball paradigm. It's very useful to test a new EEG headset, for instance. So how it works: I have boring stimuli, and from time to time, I have a deviant stimulus, like this. And when we have this deviant stimulus, we have a novelty thing we can see on the EEG, in the EEG, and this is something we can classify with a machine learning model, and we can detect when we see a classical stimulus or when we see a deviant stimulus. Okay, so I think it's over for the demo. We'll go back to the demonstration, and just to, so what you see on the console, maybe, I hope you can see it, is the debugging from the console here, from the P300 speller. And I wanted to show you also that all the parameters in the operator system demo are completely configurable here. Okay, anyway, it's just an overview of the kind of things you can do. And of course, you can plug it, anything you can do in JavaScript, HTML, you can do it. You can use, for instance, PsychoPy, which is used in behavioral science. You can use a 3JS, which is a game engine in JavaScript and WebGL, etc. And the sky is the limit. You can do whatever you want. Okay, so I think we already speak a little bit about this. So yeah, it's shipped with the Vue.js for the as a JavaScript framework, and Bulma for CSS framework, but you can use anything you want. And as we saw earlier, so you can pass some settings directly. You can pass the settings directly in the YAML file. And don't forget that any value in this can be also replaced by an environment variable. And yeah, you can, as you've seen with the demo, we can have multiple interfaces from only one graph, one pipeline, one application. Okay, so what you can do with the JavaScript is you can subscribe to data stream. We've discussed about this. We can publish data streams, events, metadata. If you lose the internet connection for a while, it will buffer the data and reconnect automatically. And everything is detailed into the JavaScript file. And we have everything we need to present stimulus on the screen. I think you already saw this slide in a previous presentation, so I won't go into details. And of course, this is something that was tested. It's not just simple guessing, but we validated that the stimulus is synchronized with a photo LED. Okay, and then just before we go into the neurofeedback application itself, just give me 1 second to show you the JavaScript API. So this is the JavaScript class. So the main information the main class you need is this one, the scheduler, which allows you to display to schedule events either at repetitive events, like for SSVP, that is, for instance, do something every every 10 milliseconds, for instance, or do this the next time the screen is refreshed, for instance, with this method, and etc. So we provide some. You can pass callback to the scheduler, and when you provide. You want to schedule an event, you will pass it a callback, and this callback, the function in the callback, will be executed when the time has come. Another thing you will often use is the IO class. And this is the one that connects, handles all the WebSocket thing, and it will connect to the WebSocket, and it allows you to send data, receive data, subscribe to topic, unsubscribe to topics, publish, commit. Okay, this is just a syntactic sugar, for instance. Commit is if you want to store data, but you don't want to send it right away. It can be useful in several cases. And you can send the event and metadata, etc. And we have an event dispatcher, so you everything IO, etc. and subscribers provide events, and you can listen to these events and react to this. And we will see how it works in 1 minute. Okay, so before we go really on the practical case, do you have any question? And also, is the screen better now? Can you read the screen?
Yeah, better.
Okay, Matteo, when you say kind of. Okay. Okay, so if everything is clear, we go to how we build a neurofeedback application. So this is a really practical use case, and it covers all we discussed until now. But first, I'm sorry, but for those of you that don't come from the neuroscience field, we just need just a little bit of theory. And so, how does an EEG work? So, an EEG records the electrical activity of the brain using electrodes placed on the scalp. Okay, so this is the skull, and we put some electrodes here. Of course, there are other ways, but if you don't want to go under surgery, usually this is where you put the electrodes. And so the brain is made up of cells, and these cells are called neurons. And neurons communicate with chemical messages, and these chemicals change, messages change the electrical potential of the cells they connect with. Okay, I don't know if it's clear, but that means if this the cell receives a chemical message and it reacts to this by changing the electrical potential of the cell. And then if this electrical potential is large enough, it can send messages to other cells and so on and so on. And of course, we can't, with an EEG, we can't, we are talking in a very small amount of volts. So under the skin, it's measured in millivolts, but with the skull, etc., it's rather in a microvolt. So it's really, really small. It's really sensitive to noise. And the thing is, we can't really measure the activity of only one electrode. So what we actually measure is when many cells, many neurons are in the same orientation. So their electrical potential is the same, and we can combine this and measure this electrical activity of a group of neurons. We don't measure the electrical activity of one neuron, but always of a group of neurons. And so, yeah, it's really basic stuff, but if you're not familiar with this and you want to go into more details, there is an excellent website and which is called EEG EDU, and you can find it on the NeuroTechX GitHub, I think. And I have also to say that the images in this slide come from the EEG 101 from NeuroTechX. So, okay, so this is the first thing. And how do we analyze the EEG, the electrical signal? So we already saw that what we get from this is time series. So individual measurement of the electrical activity during the time. And so there are different ways of measuring this. The first way, we can analyze the data in the frequency domain. And this is what we usually do when we want to, when we talk about frequency bands. You've heard about that, the beta bands, the alpha bands, etc. So we basically check what is the frequency of the main frequency of the brain activity. Of course, there are always several bands at the same time, and we can see how they relate together. And another way of analyzing EEG data is the time domain, in the time domain. And this is what we use, for instance, in the ERP analysis, the P300 speller we saw earlier. So we just check if there are spikes in our data, and if the data assume a shape we are expecting. So just a quick question. If we wanted to build a neurofeedback application, what would we use? Would we analyze the data in the frequency domain or in the time domain? Yes, Matteo. Yeah, of course, we are analyzing it in the frequency domain. Okay, so let's see how it works, how we can do it.
When does time domain work? When do you actually use time domain?
We use the time domain, for instance, when we do ERP research, when we do the P300 speller. You remember the demo earlier when the letters were flashing on the screen? How does it work? It's when the letter I'm focusing on is flashing. 300 milliseconds later, yeah, there is the spike, and this is the spike you see on the right. And so we will try to classify this in a machine learning domain, in a machine learning model. So this is one aspect, but there are many kinds of ERPs, event-related potentials, and there are novelty potentials. There are potentials when you see an error, and many kinds. There are world books about this. Okay, so for this, I will just launch this time the so you can see it also, the graphical user interface, which is still a work in progress, but it works on macOS and has everything bundled into it. So how it works, we first select the YAML file, then we click play, and then we launch a graphical interface. So just for you, so you know, for this example, I don't have a headset on me. I'm replaying a data file that was recorded. And so, okay, I'm just launching the pipeline. Okay, and then I can launch another screen. So it's just the monitoring that you saw earlier. Oh, let me check the raw data first. So this is real EEG data from the frontal zone. And if I wanted to have a basic neurofeedback application, and this is what we will check. So, okay. So this is just a basic neurofeedback. Of course, you can deduce that if we are able to display these frequency bands in a web browser, okay. So my it's finished because my data set was really small, and it's already over. But it was just an example. And yeah, so if we can display it into a web browser like this in a table, you can imagine that we can do a lot of things. We can do a game, we can do play sounds, etc., etc. So I think, yeah, I only have like 2 or 3 minutes of data, so maybe it's not a good example, but we can also have random data instead. Okay, so now we have this. Maybe we can look at the code. Okay. I hope you can see the code. Otherwise, it's on the screen, it's on the link you have in the chat. I can't find the chat. Where is the chat? Yes, okay. I'm pasting the link again if you haven't downloaded it. Yeah, Matteo, the YAML file is in the zip file, yeah. And everything you need is in the zip file. The whole demo is on the zip file, including the data if you want to replay real data, and otherwise there is a node you can use to generate random data. Okay, so the code. Okay, so this is our graph or application. So remember that earlier I've told you about a way of importing graphs. So this is an easy way to have multiple pipelines and into digestible chunks. So here I'm importing the replay, but you've seen that I have commented this, and if I uncomment this, I will play random data, synthetic data. No, it's not random. It's basically it's a sign. And just let me show you. Instead of playing random data, now I've changed. Instead of playing real data, I'm playing generated data. Oops. Oh, okay, sorry. I have, yeah, it's a work in progress, and I haven't compiled BrainFlow with this build, so it doesn't work. But it works. It works on the console. Again, it's just a POC. What's this? Yep. Okay. Okay, so now I'm building. It's a synthetic data, so it just a noisy scene. Of course, now because it's artificial data, the power bounds doesn't make much sense, but it gives you an idea of what how it works anyway. Okay, so this is the first thing, and so if I look into this, oh, okay, it's okay, but Matteo, if you look at the UI node, you will see that there is no feedback route, which is defined. That means that in a web browser, you will just call this. So let's look at the YAML file first, and then we see how we get the data into the web browser. So here I'm importing data from, okay, I will use I've lost my mouse, okay. I will use the replay data. So here I have some data coming from a Vitalino. It's not high quality, etc., but it's working for the demo. It's pretty light, so it's okay. And here I have the graph and the replay. So what we do in this pipeline, we have several nodes. First, we have a replay node, and the replay node is looking into a file at this location. In the HDF5 file, there is Bitalino section, and so we will check, we will read from this group, and we will play this in real time. So if I wanted to play the data slower, I will have a speed of maybe 0.5, and it will last twice as long. Then the thing is I need is to select which node, which electrode I want to do my analysis on. And you know, on Bitalino, it's a generic board, so they have channels have names like A1, A2, etc. And so in the file, select the A1 channel, and then I rename it. So it's a convention. So after that, I can use it everywhere, and it's called FPZ for prefrontal central. It's a standard EEG naming system. Because it's a Bitalino and it's not outputting microvolt directly, there is a small module that converts it to microvolt, and it's also an excuse to show you how we can have a custom node. And then I publish this data to a custom, to a broker with the topic row. So there is a data stream that is called row, and I connect everything together. So I connect the replay file to the replay node, to the select node to the rename node, etc., etc. One thing you may have noticed here is that there is a column and then Bitalino. This is a named port, actually. So when in the replay node I specify keys, it's a list, so I can specify as much elements that I want, as much group as I want. Each keys is generating one output. So if I want to connect to a specific output, I need to know its name, and it's defined here in the replay node. So here I'm connecting to the output called Bitalino in the replay node. And the whole pipeline is running at 10 Hertz. So by default, Bitalino is playing, I think, 1000 Hertz. So that means that each second I get 100 samples. Okay, so this is the replay node, the replay pipeline. And if I want to replace this by a synthetic board, it's kind of the same principle, except the data doesn't come from a file, but come from the BrainFlow driver, and doesn't have the same name. So Here it's called EEG_1, so I renamed it also, so we have the same convention, and I I plug it to, I publish it to the raw topic, and yeah, and so the same thing, and I can then in the main graph connect to the raw topic. Here I have another pipeline with only one node. It's the broker node, and this is the node responsible for the publish subscribe. And you have all the details. It's in the tutorial if you want to go into details about how publish subscribe work. And so the subscriber, the publisher send data to the broker retains it as long as needed, and subscribers connect to the broker and receive data according to the topic. So here I'm connecting to a list of topics, but here I have only one topic I'm subscribing to. It's a topic called raw. So it's raw data. That means if I want to do something with it, I do first have to do really some basic to clean a little bit the data. So first I apply a notch filter. Notch filter is a band stop, so it will remove part of the signal in the frequency domain. Here I'm choosing between 45 and 55 Hertz. Why? Because in Europe at 50 Hertz, we have the electrical noise. And so we want to remove all the electrical noise in the room because otherwise it really pollutes the signal. Then I'm not interested into all the frequency. I'm interested basically between 1 Hertz and 30 Hertz. Oh, maybe I should have put 40 Hertz, so I can go into the gamma range too, high gamma range. And so yeah, I leave this as an exercise for you. You can change the value 30 to 40, but of course it will work, especially because we are doing, maybe we want to do, I'm not aware of a lot of neurofeedback on applications on the gamma range, but maybe you can come with something, I don't know. Then we have a filter bank. So this is where we extract the data and the frequencies. So here we have default values. It's but you can in the literature, not everyone is agree to what it means to have alpha. So for most people, it's between 8 and 12, but sometimes it's 7 and 13 or 7 and 14. It really depends on what you can find on the literature. So you can change the values in the parameters if you want to. And so yeah, and from this we will have several output, one for each value. Then we compute the power of these frequencies, and we'll show you how it works in the custom node again. And usually we do things a little bit more elaborate. We use the Welsh method and we do average, etc. But I will show you how we can do this more simply in a custom node. And then, because we have computed the frequency powers, we will publish the data to the filtered topic. And we have also another publisher to publish the frequency bands. Sorry. So here we publish the filtered data that is after the band stop and after the band pass. And here we publish the frequency bands generated after the band powers, as you can see in the edges. So here, as you see, I subscribe to, so this is the subnode. It has an, subscribed to the raw topic. So this node publish one output per topic. And so I publish to subscribe. I connect the output called row of the sub node to the input of the notch node. Then I connect the default output of the notch node to the default input of the bandpass node. Then connect the bandpass to the filter bank to the band powers to the bandpass, and okay, the pub filtered. Yeah, bandpass to the pub filtered and the band powers to pub bands. And everything, I do this 10 times per second. Okay, so this is where we can do all the processing. So basically here in the import, we do the acquisition. Here we do the processing. And in this pipeline, I'm managing the user interface. So again, here I'm subscribing to 3 topics and I connect to them. So here I define only one route because there is already the default route. The default route is this one, monitor route, where you can see the 3 topics I have subscribed to, raw filtered bands. I can see I connect sub-row to the UI row, sub-filtered to UI filtered, sub-bands to UI bands. Okay, so that means I connect the input called row from the sub node to the UI node to the output called row of the UI node. Again, this because here I'm defining, I'm writing. I can the output node will be defined on the fly. So if I have return EG, for instance, here I would have EG instead of row. Okay, I think for this, for the YAML file, I think we've covered pretty everything. Do you have any question about this? No? Okay, then. So, oh, yes, the subscribe. Okay, so the publisher subscribe messaging system. How does it work? Publishers will write data to.
I actually just wanted to know the syntactic this thing PubSub. Yeah, I understood how PubSub works.
Okay, okay. So how does it work? Here I'm writing. I have a default. I have a publisher here, a node publisher.
Okay.
And it will write to a topic. It will this node will listen to its default input.
Yeah.
And will send data through 0MQ to the raw topic. Is that part clear or not?
Yeah. Yeah.
Okay. Then here I have. Oops. Here I have a subscriber, and the subscriber subscribe to different topics.
Yeah.
Here only one topics, and it's called the row topic. And when this node subscribe to the topic, it will dynamically generate one output for each topic it is subscribed to.
Okay. Yeah.
Okay, so that means that if I want to get data, but maybe we can see in this in the last pipelines, because we subscribe to different topics, and maybe it's more clear.
Yeah.
So this is one way. You know, there is several way in YAML to write things. So here I could also have done this. This would be exactly the same.
Okay.
And so here now the sub node have 3 outputs, actually 4 outputs, because there is always the default output, but there is nothing on this default output. And here we have 3 outputs, one called row, one called filtered, and one called bands. So in my user interface, here in my monitoring interface, if I want to subscribe to the, if I want to send the output of the sub node to the input of the UI node, I will do this. Okay, that means get the data from the output called row in the sub node and send this data to the input name, input called row in the UI node.
Okay. Got it.
Okay, cool.
Yeah.
Okay, so this is basically how we can describe the processing pipelines. And you may have noticed that we use different nodes, nodes. So here, this is nodes that are defined natively into Timeflux. So the first one here, it's in the core. This one is in the Timeflux_DSP modules. We actually have different kind of filters. So here in the same module, we have 2 classes, one called IR filter, the other one is a filter bank. And here we have, here we have custom module. And if we look into this, that means it's in the module directory, in the power, it's in the module directory in a file called power.py. So let's check this. I have a module directory and I have a power.py. Maybe I can, I would maybe start with this one, which is maybe a little, I don't know if it's easier or not, but let's take this one. So what we have in this, when we receive data, we need to transform it to in power bands. So basically, we just square the data, and this is our power bands. And this is exactly what we do here, but it's not as easy as you can imagine, because what we do, we need to take the signal and have a sliding window in this signal, and in each window we compute the the frequency bands, and then we square this to have the frequency powers. And we average this by a band. So this is a simple way of doing this. Here we can see that we, instead of extending the node, the basic, the node core, I'm extending directly the time window node. And this is a node that will take care of getting chunks of data, overlapping that data, etc. And so I can give the length, how wide is my window in terms of samples, and how much overlap there is, again, in terms of sample. So here I'm just overriding the time window class. And so we can have a look at this class. I don't know why I keep losing my mouse. Okay. So here I have generic window, and here the time window. So yeah, we have two kinds of window. We have a window that, okay, I think I've chosen the time window, yeah. And so, you know, because we are working with electronic devices, okay, Hamza, thank you for coming, and talk to you later. And so we have two kinds of windows, and one is a time window. That is, if I say maybe I want to take, I want I want my window to be 30 milliseconds, for instance. So I will always, in my output, I will always have 30 milliseconds worth of data. And the step is how much I want this window to overlap. So if I specify 15 milliseconds, each time I will have 50% overlap in my windows. And yeah, so we need to take care of a few things of buffering the data. What happens when we don't have data for a while, or when the buffer is overflowing, or etc. And another way of doing windows in the data is not using time data. It is using samplers, because we are dealing with electronic devices. So we can't expect to have always exactly the same amount of samples. If I have a device running at 100 Hertz, sometimes I will have 100 Hertz, sometimes I will have 101, sometimes 98, etc. So, but you know, for some cases, and especially if you want to do machine learning, you need to have a very precise. You need to have always the same amount of samples in your data. So in this case, if you need to have the same amount of samples, you will use the sample window. Here in our neurofeedback application, it doesn't. It's not a big deal. We can use either one or the other. But if you do machine learning or epoching, sometimes it's better to use the sample window. Okay, maybe I'm digressing, and we don't need this amount of details right now. Okay, so this is just a basic example. So here we extend the time window. That means we receive data in the update that is already windowed. And here, so don't forget that inputs and output are data frames here. and we just square the data, and we average this data. And this is what gives us this is what gives us our frequency power bands. So just for the kicks, here I can specify how I want to average the data. By default, it's a median, but we can have the mean also. It's really as you want. And here just so here it's classical pandas syntax. So if you come from the data science field, you are already familiar with pandas. If not, I really encourage you to look into this, because it will, for data science, it's really useful. And if you learn pandas, you will. It's not. It's a skill you can reinvest. And yeah, so I need to transpose the data because it's not in the same direction. But basically, it's just this. I square the data and I average what I need, and I set the default output with this, and then I have I just set my output. So it's how you would do a really simple bandpass power bands node. Any question on this? Or maybe I've lost everyone already. Why should we square the data? Because we want to have an absolute value. Otherwise, so when we square the data, we are always we are sure our values are always more than 0. Aha. Okay, so we've covered the YAML file. We covered custom nodes. There is another nodes you can look at, and it's just a transfer function that because the Vitalino, what it gives us is physical units, and we need to transform this in microvolts. So this is just a way of doing this, and it depends of the voltage, etc., and the gain. So we need this, but I will let you look into the code yourself. And the next and maybe last thing we need to see is how we connect everything into a web interface. So, okay, in the modules directory, I have my custom modules. In the graph directory, I have where I have my import graphs. And here I have some data. And oh, you know what? Maybe something you can try also later if you want. This is something we will do actually in the real application when we want to manage different kind of EEG systems. Here in the main app, you can see that I have commented the graph I'm not using. Okay, what will be really better is that this is configurable. So I don't want to have to switch to comment things each time I want to select another board. So maybe one thing I can do here is to have this, to transform this into a configurable field. So I'm not telling you exactly how to do this, but I can point you to some documentation. And also maybe again, still, oh, okay, my mouse is here. Okay, so I leave this to you as an exercise. Replace this 2 lines by only 1 line that allows you to easily switch between the synthetic board and the replay data. Okay, so not now, but you can do this when you have time. And then let's look at the JavaScript and HTML. So it's all located here in the www directory. I have the index.html file, which is, really basic stuff. What is of interest, it's this. You can see that the script is called with an absolute path because it's embedded directly in the Timeflux UI, as well as the Bulma CSS. So it's a CSS framework. You don't have to worry about this right now. Just so it's easier for the eye. And I have a custom CSS. There is almost nothing in it, but just to enhance a little bit the visual. And the main logic. Yes, exactly, Matteo. And the whole logic of the application is in my custom app.js file. And the rest is just, it's just a big table where with IDs that I can get. And you can see I have my 5 frequency bands. And I have a progress bar, etc. Where is it? It's here. Okay, so if I look at the JavaScript, there are a few things I do here. So this is just a JavaScript idiom saying I want a strict syntax and send an error if my syntax is not orthodox. Here, I connect to the WebSocket. So I have the IO class is defined in the Timeflux.js API. I subscribe to the bounds topic. Remember, we defined the bounds topic here. This is not strictly useful, but this is something that you can get inspirations on. The IO provide different events. So there is a connect event, a disconnect event, an event, etc. And so it's useful if you want to enhance the graphical user interface, maybe having a small I don't know, LED here, green when it's connected, red when it's not connected, or something like that. So you can subscribe to this event. Here, it does strictly nothing except displaying something in the console. Here, it's interesting because this is how you would pass settings from the YAML file to the JavaScript API, so you can receive a configuration directly from there. And how you will do that? Yeah, everything is in the zip file. Yeah, maybe it's blurry. And in the YAML file, I don't think I have I don't have configuration here. But let me check. If you remember, I had this. Where is my mouse? Okay. I think it was in the operator. This is a good example. So you see, for each, I don't have any parameters here in this neurofeedback application, but I can provide any kind of settings. So this is how you would do this. You would do it. You will pass settings. So this example, you can find it in the example directory of the Timeflux _UI plugin on GitHub. So here I have some routes, and I can define. I can define settings for each route. And here I have an object called field, and I have a list called events. So what if I wanted to pass a parameter to my neurofeedback application? Sorry, I would do this like this. Settings, neurofeedback, because I can have several applications at the same time. And I would have something called foo bar. So I have an object, a settings object, which will contain only 1 and 3, where the key is foo and the value is bar. So what will happen when I play this? Oops. Okay, and for this to work, I have to switch the console. Okay, so 2 things you can see. First, here we have the connected message we got when in our callback. Keep losing my my mouse. I think it's because I'm presenting or something. So here I can just use my keyboard, I guess. Here, this is where I'm displaying the connected message. And here, this is where I'm logging and displaying the settings I've set in the YAML file. And I can see I have my settings here. So this is where how you can pass parameters from the YAML file to JavaScript application. You can see that the WebSocket connection has closed because we reach the end of the file, and so there is no more data, and so Timeflux excited because we were replaying the file from Vitalino, but maybe if I don't want this, I can just replay the synthetic data and it won't exit. And again, it was disconnected, but detected that it got a new connection, so it just reconnected. And it's resent all its subscriptions, etc. So everything is kept in memory. So don't worry if you lose connection, and it will always be able to restore its state. So yes, okay. So we saw how we connect to the WebSocket, how we connect to the publish subscribe to the bounds topic. Yeah, just as an example, how we can have an event here, how we can do something with settings we would want to pass. Here is just we just get some in JavaScript we get the DOM elements of the table. So you see that each one has an ID, and so we are requesting the ID of this table, so we can keep this into memory and avoid requesting the DOM each time we refresh data. And here it's a method of the IO instance. So we receive an event. So each time there is something happening in the bounds stream, we get the data and we do something with the data. So here, what I do first is, so it's the data is a matrix, so it has several lines and several rows. In this case, I think, don't remember exactly, but what's the refresh rate, but I think it's 1 per second or something like that. So we won't have a lot of data, but sometimes you will have a lot of data. So you don't need to refresh, to loop into each row. So here I just keep, just want to display the value for the last row. What I get in the data is the absolute value of the power band. And this is an interesting value by itself, but sometimes it's not really meaningful also, because it depends of the EEG amplifier, it depends of the subject, etc. So most of the time, what you want to do is analyze the relative amount of one frequency band compared to another frequency band, for instance. Of course, here it's artificial data, so I have lots and lots of delta value, and everything else is basically just noise, but it's not representative of real data. And if you remember the Vitalino data, it was much more homogeneous. So what you want to do then is to compute the relative power. So this is what we do here. So we have the absolute value in microvolt, and here I want to know how much I have. So here I have 94% of delta, 1% or 2% of theta, etc. And so for this, I need to add everything together and then compute the relative values for each frequency band and just update the HTML table in JavaScript. And this is how you can do basic neurofeedback application. Okay, so okay, do you have any question before I'm giving you some homework? Exactly, Matteo, but that's part of the homework. I can't do everything for you.
Yes, one thing also, yesterday I was in a meeting with Bhargavanti and Mohit, and they were asking me questions about Timeflux capabilities from a DSP point of view. I was not able to answer. If they could like do to you like the same questions or like express like yeah, they were interested in like which kind of DSP nodes are available, for example, for denoising. If probably it's already shipped and there's no need like to redo the usual stuff. I don't know, but I would like them like to ask you things, because I know yesterday were really terrible with me. I couldn't answer any of their question, and now it would be I think it's the time if they could like find, yeah.
So yeah, okay. So first of all, you can find the list of the available nodes, if I can get a browser, yeah. Here on the documentation website, there is a plugin called DSP. And in the API reference, okay, Daniel, I will come back to you to this just after this. And so, yeah, we have some, the list of the DSP nodes are, you can find them there, here. There is some filters. So each time we try to provide some documentation on how the filter work and what it does exactly. So we have so first, sometime you want to downsample the data because you have data rate of 1000 hertz and you don't want to work with so much data for some reason. And so one way of doing this is dropping rows. So this is how you can do this. All the parameters are explained, and we try to provide example when we can. There is resample node, so you can, it's another way of decimating the signal to downsample it. We have a classical IR filter to band pass, band stop, to extract frequency bands, etc. And so everything is based on the SciPy module, the IR filter, a function of SciPy. So there is some documentation you can find. So for instance, here it's just an example of how you would filter a noisy signal. We have a fear filter. We have things to scale the data, to etc. etc. We have filter banks. We have a collection of helpers, maybe not here, but we have also much more in the utils helpers. I will leave you look into this. We have something to detect peaks into in a signal. So there are many ways of detecting peaks and through in the signals. So depending on how is your data, what kind of data you're analyzing, etc., etc. And so we provide a few methods to use this. The local detect is one method I like to use. It's very effective for ECG data, for respiration data, this kind of thing. And so here is we explain how the algorithm work, etc. We have another way of detecting. We have 3 ways of detecting peaks in signal. So we have some nodes to DSP algorithm to have to detect the quality of the signal. And we have also, of course, nodes to denoise in the frequency domain, so basic Fourier transform. Okay, Vij, thank you very much, and yeah, we can talk later, so no problem. And so yeah, you can do a FFT. Okay, so I didn't want to show you this node because that was part of the homework. But okay, here is a Welsh node. I won't tell you what it's about. And another node to compute frequency bands, another way of doing it, etc. We have tools to detect delays, etc. And also, so if you want to denoise the signal, for instance, for detecting eye blinks, for instance, we are there are a few ways of doing this, but basically it's involve machine learning. So you will need a way of either detecting to have a data set with a typical artifact that you would classify, and then you would detect this in real time. So there, I won't enter into the details of this, but there are several ways of doing this. And also what we are working on is it's not published yet. It's not on the main repository, but it's still public. Oh, I'm not sure what. I think it's this. Yeah. And where did she put this? So this is a Raphael repository. Okay, so we are basically implementing. Oh, okay, it's the first one. This. So this is a very common algorithm, very famous algorithm, which is called artifact subspace reconstruction to denoise the signal, and it's working. Okay, I can't enter into the details. There are all the documentation here. I invite you to read about it. And basically, we need 1 minute, 30 seconds to 1 minute of really clean signal at the beginning, and then we will clean automatically any artifact. So the original algorithm is much more for offline use because it's really heavy. And for online usage, we are working on Riemannian version of this, and it's still a work in progress, but we have good results on this, and this is a work sponsored by a French university, and we have a few people working on it, and hopefully we will be able to release this in next month, probably. And yeah, so this is one way of filtering the data. Okay, then, oh, sorry, first, Matteo, Bar, etc. Oh, Bar is, no, Bar, you're still there. Does this answer your question about the DSP nodes, etc.? Okay, cool. Okay, Daniel. Okay, so for the structure, basically you do whatever you want. I use this simple convention, but honestly, you organize things exactly the way you want. The main thing is, so in the app YAML, in the UI, what I just need to do is to map at one point, to map the directory where my index.html is. So here it's www, it's here, and it's neurofeedback. So it means when I go to localhost / neurofeedback, it will point to the www directory here. This is the structure I use, but you can organize this the way you want. There is no, basically it will add everything in the path. So it will first look into for instance, for the custom Python module. I think it's in this graph here, for instance. So it will look for a modules in a directory somewhere directly in the path, then in the subdirectory of where the app.yaml file is, and in the www the directory where the index.html is. So it will basically it will explore things, and we'll try to, and in the current directory that is where the Timeflux is executed also. So the working directory. So it will add everything in the path, and find where automatically find where the custom Python modules are located. And yeah, I don't have much advice to give you. It's not fixed. I think it's good to have conventions, so we all agree, but then you can do whatever you want. Okay, so I'm not sure to understand them. So do you mean you fixed your issue?
Yeah, because when I made the demo file, it couldn't, of course, it didn't have a www folder to generate the index HTML.
Okay, but which demo are you?
Just from the first one of Hello World.
Oh, okay. Oh yeah, but in the Hello World there is nothing to display on the. In the Hello World demo, I remember that there is no.
And on the second demo there is. You can.
Okay.
But,
oh yeah. So
but in the documentation you don't. You know. I didn't clone or download the repository, so I didn't understand that it needed additional files.
okay.
So if you go down to the last one, right? I mean, maybe it said it in the text, but it doesn't. I'm pretty sure that it didn't say anywhere that you needed to have the WW files.
Here in this example, you should not, because
you should not. In fact, you don't. If you run the second example, and then so Timeflux and then name of the YAML file, that is timeflux_ue.yaml in this case, then it runs in the terminal, and then it opens the localhost at port 8000. And then and there's no need for any other folder on your local drive.
It didn't work for me.
I will come and fix that to you on next week. But you should be able to run out of the box. I did
But it works fine if you put it in the folder and add the WW folder. So.
But when you put what into the WW folder? You mean this example? Yeah.
No. I made a new folder called Hello World, and then within Hello World, I put in the basic WW folder, and then I get in the terminal window the local host address. But if I don't have that, I can try again maybe.
But what are you displaying? Are you using the monitoring node, or it's a custom JavaScript application?
No, just using a basic monitoring node.
Okay, so the basic monitoring node is embedded in the Timeflux.ui. This is the only one you don't have to declare.
Okay, maybe I had some troubles with it. Okay.
Maybe you have first to install the UI
module. It's installed.
Okay.
But all right, I can show it to Matteo. That's probably the easiest way to fix it in the future.
Okay, and if you find also maybe I have some errors in the documentation. So if you find something that's not working properly in the documentation, please open an issue. And,
sure, yeah, no problems. I mean, we have to decide what's human error and what's not human error. So, but it seems to be working fine now. So.
Okay, cool.
I'll play around with it and see if I move the WW folder, if it'll still work.
Okay.
So it might have just been a long journey, but thanks for the session today. Very interesting and relevant, and I look forward to playing around some more with Bitolino next week.
Cool.
So I guess we'll be in touch. Thanks everybody. I got to run.
Okay, thanks.
Have a good weekend. Bye.
Later.
Take care. I look forward to the video too.
Yes.
Cool.
All right. See you. Bye. Have a nice weekend.
So, Bar, in terms also in the workload of application, it really depends of your pipeline. So it depends how heavy the processing you're doing, but basically it's just Python and pandas, and it's each pipeline run into its own process, so things are running in parallel. But I don't have a definitive answer to offer you, because it really depends of the processing you're doing. And okay, any other question? Okay, and if not, we can, and if you have a question later, feel free to come to the Slack or to the Discord server, and we'll answer this. Okay, and next and last thing. So this is an example, a practical exercise how to do some basic DSP with Timeflux, and I'm inviting you to go there. And you can find this. Hey, now I'm pasting the link. Okay, give me 1 second. It's an exercise that was done by Raphael, which we used this into in a hackathon. Huh. If I can find my mouse again, okay. And here. But you understand why I had a bitly shortcut. Okay, so this is something you can do. Basically, you have two signals. You need to sum these signals, and then we will remove the noise to get back to the original signal. So I invite you to look into this example and to play with the example, and if you have any question, you please come and express them on Slack or Discord. All the things we can, so we have a very basic demo, and we can do a lot of things to improve this demo. And according to your profile, you can work on several parts of this. So maybe you are a neuroscientist, and what you could do is imagine what kind of neurofeedback we could implement. So should we do just alpha neurofeedback, or maybe have a ratio on between alpha and theta somewhere, or etc., etc. So what do you think we should do? On which frequency bands? At which location? And when I mean location, also maybe we also need to think about the consumer market, consumer EEG. So we don't always have a full headset with many locations. So maybe we are limited to frontal location or temporal location. So what can we do with this? And maybe also we can think of adding other biomarkers like respiration or heart rate or EDA, etc. You know, the new Muse, it has a PPG also, so maybe we can explore this to do things. So with the PPG, so we can have the heart rate. It has also a gyroscope. So with the gyroscope and the PPG, we can infer the respiration. So maybe you have some idea. We can what can we do? What can we build in terms of neurofeedback applications? If you are a backend developer or if you are a DSP engineer, okay, I've shown you a simple way of computing the power bands. Maybe you can think of another way of doing this. I've already gave you some hints, but how would you detect blinks? Okay, honestly, for the blinks, there are many ways of doing this. You can do it the hard way, using machine learning, etc. You can maybe think also that when I close my eye, I already have a spike of alpha. Maybe also when I close my eye, it's a motor, it's a muscular activity. So there will be a spike in the time domain. So, okay, how would you do this? And the Welsh methods is a better way also of doing frequency bands. And I leave you this as an exercise. And also maybe, as Matteo suggested, maybe, we can find a way of detecting, of computing the relative bonds in Python rather than JavaScript. So how would you do this? And if you are a UX designer, what would you do to improve the demo graphically? Maybe you don't want to use JavaScript or HTML at all, and maybe develop a Unity game. How would you proceed for that? If you're a sound designer, again, at some point, maybe you will need to use the OSC Open Sound Control protocol to communicate with your music player or something. What would you do? How you would design pure sound neurofeedback without image, nothing, just sound. So these are a few exercises. I think also earlier we talked about something else we can do is remember the here in the main application YAML, we have two lines. What would you do to have only one line and make this line configurable? Okay, I think that's about it. So thanks a lot. It's 5 and so I think the timing is good. So cool. So thank you very much. It's I really appreciate to have you on board. And please, if you have any question, come to the Slack channel. If I'm not here, there is Raphael, there is Sylvain, who will be able to answer your questions. And I'm sure we can, we all have different backgrounds, different sensibilities, and we can be creative together and complement each other and do amazing things together. So thanks a lot. Thanks for being there. Thanks, Matteo, to bring everyone together. And
thanks to you, Per. And I'm sure we'll do. Probably now we should to try out and do some experiments ourselves, and then maybe we can exchange some YAML file and do some questions on your Slack channel and in Discord and things like that. And yeah, I will start and playing around, and I think we can we might spend some time on our exercises, and then once maybe things like questions will raise up, or let's say direction, and then based on that we can schedule the next workshop. I might suggest to wait a couple of weeks before we do that, so we have the time to digest and get good in the basic stuff that in the things that navigate a bit the complexity of this of Timeflux ourselves, so that the next time we might use your time with matching some improvement and these kind of things. that's it. Thanks so much. It was great.
So yeah, thank you again.
Yeah, thank you so much also, because it was really, really patient of you. And I think coming from like a non-programming background, knowing a little bit of Python, it was really, really in-depth stuff about how you broke down, for example, when you spoke about ERPs and how you spoke about when you do 60 hertz per second and how you sort of get your window to refresh 60 times in a second. You know, so small details like that is so essential to explain to a layman. Even I wouldn't understand it when you broke it down. And so I think it's really, really amazing that you had all this patience to sort of break it down, and really appreciate that. And I think it'll be interesting to sort of work with it. And again, coming from a non-programming background and knowing a little bit of Python, I think you hit on notes that I already worked on, was the Welsh method and like a butter bandpass filter, which is awesome that you're already you integrated that. So, but thank you again for this.
So thanks, Sachin. And yeah, if you, but you know, there is work for everyone, even if you don't come from a programming background. So I'm sure we can use your expertise on neurofeedback, etc.
Mm-hmm. I'll be glad to help in some way.
Yes,
Okay.
time to work ourselves and have yeah, and explore like the possibility. And then I'm sure we will come back to you and bother you and your friends with a lot of questions and practical question about we will start building things and try out stuff in Timeflux. And by the moment, have a good Saturday and weekend, all of you. I think we will stay in touch.
Sure. Okay, cool. Thanks, Matteo.
We are done.
Bye. Cheers.
Bye, guys. Have a good weekend. Thank you.